I'm going to be starting on the side that says parent function, so it should be on the back, I believe. All right, so essentially all that. Yes, ma'am. Oh, one more. So essentially what this does, this activity was supposed to do, technology actually worked in our favor, but that's okay if it doesn't, was, ladies, stop talking. So what it's supposed to do was to show you guys kind of how when you add or subtract things to certain parts of the function or multiply things to it, how it transforms the function. All right. Essentially, it's just a set of rules that you just have to know. Um, but before we can even do that, we actually need to know the different types of parent functions because a part of transformations is that you're doing it to actual types of functions, so not just like f of x. All right, it's actually going to be like a quadratic function or an absolute value function or a square root function. All right, so you need to be able to recognize them as well as recognize their graphs. All right, so we're going to go through just the basic parent functions. The ones that I highlight are the ones that you definitely need to know. There's some on here that, like, if you know them, great, but you don't necessarily need that for this unit. All right. So, starting with the first one, linear. You guys have been doing that since Math 1. All right. That was probably the first function you ever learned. So, linear functions. It's parent form, which means original form, because think about it. Parent, child, who came first? The parent. So, parent means the original, all right? It hasn't been transformed yet. This is like its prime state, all right? So, linear function, its parent form is y equals x, all right? If it was transformed, we may include a slope, so like times 2 plus 5, things like that, all right? But since it's not, this is what it looks like in its more natural state, so to speak. All right. Now, you should also be aware of this one as well. The graphs of parabolas, so quadratic. You guys did a lot with this in Math 2, a little bit in Math 1, but with quadratic, its parent form is simply y equals x squared. So if you ever see anything squared and there's no bigger exponent than a square, it's most likely a quadratic function. All right. Now you probably have seen a cubic function before, which is the next one, but this didn't have a proper name to it. So cubic, its parent form is just y equals x cubed. Exponential, you dealt a lot with this specifically in Math 1. Now, exponential is a little bit different because since the x is in the actual exponent, the base or the b value is going to actually be a number. And that number is typically going to be greater than 1. So it may be, for example, 2 to the x power or 4 to the x power, something like that. But you just need to recognize that exponential is going to be some number raised to the x power. That's its base form. All right, more often than not, like for example, this graph I believe is 2 raised to the x power. All right. Now, why can the base not be 1? So just think about it for a second. If 1 is the base, 1 raised to any power is always what? 1. Because 1 times itself a bunch of times is still just going to be 1. All right, so that's why the base cannot be 1, because at that point, it's just a constant function, meaning it's just going to be a straight line. All right. Now, rational, you don't necessarily need to know, so I'm not going to highlight it, but we will be dealing more with this in Unit 4, so just know its parent form is 1 over x, But again, in terms of this unit, you're not going to be transforming a rational function. But that's also what the graph looks like. Again, you'll see that again in unit 4 when we actually do our rational function unit. Then there's the integer function, which I like to call the step function, because it literally looks like a stairwell. It just goes up in steps. Again, you don't need to know this one per se. Like, it's just nice to know, but I'm not going to ask you to identify it. Now, absolute value, you absolutely need to know. All right. So absolute value, it's that nice V-shaped graph. So x squared is typically your U shape or parabola. Absolute value is your V shape. It's typically, its parent function form is y equals the absolute value of x. All right. Radical function, specifically a square root. So this is a radical dash square root. So if I asked you what this was, I would just say it's a square root function. All right. Because, as you see the one below it, there's another one that's technically considered a radical function, but it's a cube root. So if you just see the square root symbol, it's a square root. But this is its parent form. Y is equal to the square root of x. Cube root. That's another one you should probably recognize. So the only difference between that and a square root function is that little baby 3 in the upper left-hand corner of the radical. All right, that's what differentiates is a square root from a cube root. A cube root will have that little number, square root won't. Logarithmic functions, we're not going to deal with that until the next unit. Like the whole next unit is just on exponential and logarithmic functions. So that's its standard form. It's log with base b of x, but I don't expect you guys to know this right now for that. So that's not really what I want you to know. This is another type of rational function. It's the inverse squared function. Again, you don't really need to know this one. You'll see it again with our rational function unit, which is unit 4. And then lastly is the constant. So remember, a constant function is just any type of function where it's just y equals some number. All right? So if y equals some number. So it doesn't necessarily have a parent form because since it's, I don't know why that's shaking, but okay. But since it's equaling to some number, that number could be any number. It just means it's going to be a horizontal line. That's all the graph is going to look like. Now, some things that you may want to note if you're trying to recognize the function from first glance. Because once we start transforming them, the notation may start getting a little fuzzy and you're thinking, oh, what type of function is this based off of what you see? The biggest way to note this is by looking at some tells, as I call them. All right. So for example, a linear function, you would not see an exponent. You would only see an x because the exponent is just 1. All right. That's the tell. There's no exponent, but there's an x. That would be a linear function. Now, quadratic, you will see something raised to the second power, so something squared, and there's no higher exponent than a square. So you wouldn't see like a cube, you wouldn't see a fourth power, you wouldn't see a fifth power. The highest power you would see is a square. If you see that square in there, it's quadratic. Cubic, same thing, but with 3. So the highest power you will see is something raised to the third power, or cubed. That's its tell. An exponential, x is just in the exponent. If x is in the exponent, it's automatically exponential. Absolute value, obviously the absolute value symbols. So those 2 straight lines, if you see those 2 straight lines, it's absolute value. The square root function, obviously you'll just see the square root symbol. So if you see a radical and there's no little tiny number written outside of it, it's a square root function. And lastly, the cube root function, you should recognize it by that cube root. So it's a radical with that tiny little baby 3 in the upper left-hand corner of that radical. If you see that, it's a cube root function. And then obviously constant, if you just have y equals some number, there's no x anywhere, it's obviously constant. Now, why is that important? Because when we start getting into the transformations and the rules, like I said, we're not just doing it in terms of f of x, we're doing it in terms of these actual functions. So knowing what these functions are and what makes them these functions is important. Like for example, if you don't have that square in a quadratic function, so like something squared, it's not a quadratic function. All right? It's a linear function at best. Or same thing with a square root function. If you don't have that square root symbol, it's not a square root function. All right? So having that notation is very, very important. I can't tell you how many times on a test, especially with quadratics and cubics, they forgot to raise it to square it or cube it, and I had to take off points because it technically wasn't the correct type of function. All right? And you may think that's nitpicking. It's really not. All right. So that's the types of parent functions. Now let's talk about the different types of transformations. So look on the other side of your graphic organizer. So first things first, we're going to talk about just the basic rules for transformations in terms of the order that you should typically look for transformations. All right. Now, so all of these are going to be in terms of f of x. However, to kind of help you see it a bit better, I'm also going to do it in terms of a current parent function. So the one that I chose was, we're going to do everything in terms of y equals x squared. And we're just going to make up some numbers just so you can see it. All right. So first things first, when you're looking for transformations, all with transformations, with any type of transformation, how I put it is it's typically a matter of what type of operation is being applied here. So addition, subtraction, that's typically a translation or a shift. Multiplication is typically a dilation, which means vertical or horizontal stretch or compression. And a reflection is just typically a negative being multiplied somewhere. All right. Now, it also depends on where those operations are taking place, what I like to call inside or outside the brackets. Now, what do I mean by brackets? And I would make a note of this. So, for each parent function, there are different types of brackets. All right. So, for a quadratic, it'd be parentheses squared with the x inside. Same thing with cubic, but it'll be cubed instead of squared. Then for absolute value, it's the actual absolute value symbol. For a exponential, it'll be up in the top with the x and the exponent. Then our radicals, square root and a cube root. So if I ever mention inside or outside the brackets, I mean within these different things, depending on the type of parent function it is. And these are the ones that you will typically see. All right. So for example, if I said you're adding inside the brackets for a square root function, it'll be under that radical. If it was outside, it would not be under the radical. All right. Does that kind of make sense? So that's why I want to do this in terms of x squared, because typically on tests, that's the one that I see students struggle on the most, the concepts with cubic and quadratic and how you have to put parentheses there. All right. So first things first, whenever we're looking for transformations, we first want to look for its horizontal translation, which just means you're sliding either to the left or to the right. Now, this type of transformation will be strictly inside the bracket, all right? So both of these will be inside the bracket. Now, if you are adding a number to x inside the bracket, so C stands for constant, that's a number, all right? If you're adding, that means you are going to the left C units. So, for example, with the quadratic one, let's say that C equaled 2 in this case, all right? I would write this as x plus 2 all squared. Notice how that plus 2 is with the x and the square is on the outside. It's not just connected to the x. If the square is only connected to the x, that's considered outside the brackets, even though there's no parentheses. All right? Now, on the opposite side, if you subtract c, or subtract a number inside the brackets, you're going to the right c units. So that means it'll be x minus 2 all squared. Now, you may be wondering, well, wouldn't left be minus and right be plus? Because on a number line, left would be negative, right would be positive. Yes, but these pluses and minuses come from a formula. So, for example, the vertex form of a quadratic formula looks like this. This is literally the formula for a typical quadratic function. All right. Notice how the minus is in the formula. Meaning, if I were to plug in 2 there, would that minus still be there if I just plug in a 2? Right. So if I was going right 2, I would just plug in the 2 where the h is, and then it would still be negative. But if I was going left 2 or negative 2, that means it'll look like this. And what happens there? Right, they become positive. 2 negatives next to each other, that's positive. So that's where that plus and minus comes from. Because it's literally in the formula, and it's like that for all of the parent functions, I'm just using quadratic as an example. Because it's like that in the formula, we have to keep it like that. Now, there's a mathematical reason of why it's like that, but I'm not going to go into it because you guys don't need to know it. All you need to know is that right is minus, left is plus. Okay? That's the biggest thing. So in other words, just think opposite of what would logically make sense. All right? All right. After we do the horizontal translation, we then deal with the stretches and compressions. Another name for it is dilations. So in other words, making the graph wider or thinner. That's pretty much what that means. Now, with stretches and compressions, it can be either inside or outside of the brackets, depending on what type it is. So if we're dealing with a vertical stretch or compression, doesn't matter which one, we're multiplying a number outside of the brackets. So this will be outside of our brackets. Now, how it affects our graph depends on what type of number we're multiplying. So if we're multiplying a C value that's greater than 1, so 2, 3, 4, 5, 3 halves, something like that, it's called a vertical stretch. Now, if our C value is between 0 and 1, what type of number is that if it's between 0 and 1? It'd be a decimal or a fraction. So in other words, it would be a true fraction, meaning numerator is smaller than denominator, or it would be a decimal where your ones place is 0. So like 0.5, 0.25, like that. So that would give us a compression, which just means shrink. Now, how that affects the graph, I like to use rubber bands to kind of represent it because it's really easy to see with the rubber band. So pretend that this rubber band in my hand, the way it is right now is its parent state. Nothing transformed yet. Now, if I stretch it vertically, what happens to the graph vertically? Did it get thinner or wider? Thinner. Now, back in its normal state, if I compress it vertically, did the graph get thinner or wider? Wider. So that's a way you can think about it if you want to know, okay, is it supposed to look wider or thinner? Think about a rubber band if you were stretching it vertically or compressing it vertically. All right, so if it was a compression, it'd be wider, stretch would be thinner. Now, since we're multiplying it outside the brackets, that means the y values are going to be affected by that. So if you had to do it by hand, all you would do is multiply the y values by that c value. So what this would look like in terms of x squared? You would see 2x squared. That's one way you'll see it. Or let's say I threw in a translation in there. It would be 2 parentheses x plus 2 all squared. All right. So the 2 would be outside of the parentheses, or if the x squared was already connected to the x, this would also be considered outside. All right. Now, horizontal dilations, that's where it's inside our brackets. So very similar to vertical, but instead of multiplying it outside of our brackets, we're multiplying that c inside our brackets. Now, I like to say that vertical and horizontal are the opposite of each other. So while if we're given a fraction for vertical, we have a compression. For horizontal, we have a stretch. Now, if it's greater than 1 for a horizontal, then we would have a compression. Now, how I would think about this, okay? Still looking at my rubber band, but now I'm going to be stretching and compressing horizontally. So this is it's its parent state. If I stretch it horizontally, what's happening to the graph horizontally? It's getting wider or thinner? Horizontally. Wider. So horizontally, when you stretch it, it gets wider. Whereas if I compress it horizontally, what happens? It gets thinner. So if you notice, even though the name switched, compression, stretch, compression, the numbers associated with do the same thing to the graph. So if it's a fraction, your graph gets wider. If it's a number greater than 1, and what I mean by greater than 1 is don't worry about the negative. All right. So if it's like not the actual fraction, like a true fraction, so that qualifies as greater than 1, it is thinner. Now, you do need to know the difference. Yes, ma'am. Yeah. Now, you do need to know the difference between the stretch and compression, be able to identify it. So again, if you get confused with that, you mainly need to know that fractions make it wider, whole numbers or bigger numbers than 1 make it thinner. And then if you know that it's inside or outside the bracket, you can determine horizontal or vertical, and then you just got to ask yourself, okay, if I know it's a vertical dilation and it's getting wider, do I need to stretch it vertically to make it wider, or do I need to compress it vertically to make it wider? All right, that's what you should want to think about when you're thinking about this. That's why I like the rubber band example, because it's actually a visual of what it would look like. All right, does that make sense? So for horizontal dilation, all you would do is since it's affecting the x value, it would divide the x values by our c value. Now, what it would look like, it would look something like this. So let's say I had 2x plus 3 all squared. That 2 next is multiplied to the x. That represents my horizontal dilation. Any questions on dilations? All right, then we have reflecting. Now, reflecting is really easy because it just means there's a negative slap somewhere. It's multiplied either outside the brackets or inside the brackets with the x. That's the only difference. So that's why I said with dilations, don't worry about if it's negative or not, because that's where the reflection comes in. So, first off, if your negative is inside the brackets being multiplied to the x, all right, that means you are reflecting over the y-axis. Because what's happening is that the x values are changing, but the y's are staying the same. So you would multiply the x values by -1. Because remember, if you flip over the y-axis, so let's say that this strip right here is the y-axis, and I started over here. Positive y's, positive x's. But if I flipped it over here, the y's are still the same, but the x's are now negative because they're in a different quadrant. All right. Now, the opposite would be if you had the negative outside of the brackets. All right. If that negative is outside of the brackets, you're reflecting across the x-axis. So the y values are what's changing. So in other words, you would multiply the y values by -1. So what this looks like if it was with an actual parent function is that, let's say I had -2x squared. Nope, that's wrong. It would be here. -2x squared, or it could be -2 times x plus 3 all squared. Since that negative is outside the brackets, and yes, in this case it is considered outside the brackets because there's no parentheses around the x, you have to assume it's outside, then that is over the x-axis. Whereas over the y-axis, it would look like this. -2x plus 3 all squared. So the negative is inside the brackets being multiplied to the x directly. All right, the last type of, yes, sir. Yes. Now, the last type of transformation that we have is the vertical translation. So we already know how to translate horizontally. Now we're doing it vertically. And that's just going up or down. Now, both of these are strictly outside the brackets. All right. And these are the ones that make sense logically. So if you're going up, you're adding. If you're going down, you're subtracting. These are the ones that make sense logically. So if you add C or a constant, you're going up C units. Subtract C, you're going down C units. So an example of this would be x squared plus 2. That is technically considered outside because the 2 is not included in the square. It could also be x plus 2 all squared plus 3. That 3 is what's outside the brackets. So that would be where the vertical is. Shifting, same thing. X squared minus 2 or x plus 2 squared minus 3. Both of those would be considered outside the brackets. We're almost done with this, and I'll give you guys a 5-minute break. I know you guys are kind of crashing out a little bit. All right. So on the test, I will most likely let you use this table, but it's still something that you need to kind of recognize because you will see it again in some other units. All right. Now, let's look at an example of what they already did. So they already told us what all of the transformations were for this function right up here. So this function up here has 4 different transformations. Now, this is what type of function? What's the parent function? Or what's the function called? What type of function is this, guys? What's the key feature that it has? It has a square root, so it's a square root function. That's why I said recognize what the key feature is. The key component, as I like to call it. That's the tell. All right? So this is a square root function. Now, we start with our horizontal translation, which is right here. We're adding 3. Thus, we're going to the left 3 units. We then look at our dilation. It's right here, this 2. It's outside the brackets, because remember, the square root symbol is considered our bracket in this case. Thus, we are stretching, because it's greater than 1, by 2. All right? It's a vertical stretch, technically. Then we have our reflection, which is this minus. It's outside the bracket or the radical symbol. So that means we're reflecting across the x-axis. And then lastly, we have this +1 on the outside of our brackets. So that means a vertical translation, which we're going up 1. It's like a dark green. Yes. All right, any questions on this? And we're going to do some examples when you come back from your break. All right, so I'm going to give you guys a 5-minute break. I'm going to set a timer. You need to be back before that timer's done. All right, so you can use the restroom, but no tomfoolery. And yes, I did say tomfoolery. All right, guys, break's over, so we're back to the grind. All right, so you need your packet out. We're gonna be on page 3. So we're gonna do some examples now. So take your packet out, page 3. You may want to keep the graphic organizer on your desk because you may need it for reference. So packet page 3. Come on, guys. All right. So we're gonna do a couple of examples with how to write out a function if they give us the words of how they're being translated. They tell us the parent function, they tell us how it's being translated, so we're going to actually write the function. Now, I don't really care too much about matching the graphs right now because honestly, if you can write out the function, I let you guys use Desmos on your tests anyway. So literally all you have to do is put that function in Desmos, match the graph. All right. So I'm not too worried about the graph identification. I'm more worried about can you actually write the function out. All right. So first things first, it gives us the parent function f of x is equal to x squared. And it's going to be shifted right 3 and shifted up 2. So first off, because you do need to know how to identify them, what type of function is this going to be? If the parent function is x squared. Quadratic. Good. All right, so this is a quadratic function. So what I typically start with is I just go ahead and draw the brackets. So f of x will equal something x, guys, all squared. I'm leaving enough space in case I need to add anything inside, outside, whatever. All right. This is how I would typically start writing these functions. Now go ahead and put your brackets, leave a little bit of space, and if you need to shorten that space at the end, that's fine. So First, we got to talk about shifting right 3. So first off, we're going right. So are we talking about inside or outside my brackets? Inside. So we're going inside the brackets. A way to remember this is that if you're going right, left, that's the x-axis. It should be directly affecting x. If it's outside, that means it's affecting y. All right? Which makes sense because up, down is the y-axis. Now, we're going right 3. So what type of operation are we going to be doing? Addition, subtraction, multiplication? What do you think? Subtraction. Good. So inside my brackets, I'm going to put -3. Then shifted up 2. So am I talking about inside or outside the brackets? Outside. What type of operation am I doing? It's a vertical translation, but what type of operation? So addition, subtraction, multiplication? Addition. We're going to add that 2. Remember, right to left is the one that is the opposite of what logically makes sense. Up, down is what logically makes sense. All right. So this would be our function. We've done all the translations. So if you can get this far and you had to match the graph, all you would do is put that exactly into Desmos and match. All right. Based off of what it looks like. All right. Any questions on number 1? All right. Let's look at number 2. So here's our parent function. It's 2 raised to the x power. So what type of function is this? What's a key point? What's its tell? It's exponential. Remember, its tell means that there's an x in the exponent. That's its tell. So it's exponential. Remember, and I showed you guys this on the parent functions, all of these functions have a tell that will tell you what type of function it is. So if you can recognize what the tell is, you know what type of function it is. All right? Now, this one is being reflected over the x-axis and shifted down 1. So first things first, I'm just going to write it out to where I can see the inside and outside of my brackets. So we still have a base of 2, and then the brackets are going to be up here. Now, if it's outside for exponential, it's technically not in the exponent. All right. So first off, reflecting over the x-axis, that means I'm making something what? Or I'm multiplying something by a what? What denotes reflection? It's one symbol. A negative. A negative is what denotes a reflection, whether it's over the y or over the x-axis. The spot of where that negative is determines it. So if we're going over the x-axis, meaning the x's stay the same, the y's change. Would it be inside or outside the brackets? Think about it. The y's change. Outside. Good. So outside would be right here. And I was just putting this 2 in parentheses so you know that negative is being multiplied outside of that 2. So it's just kind of an afterthought. Now, it shifted down 1. So we're going down. Does that mean I'm going to be inside or outside the bracket? Outside. And what operation will I be doing? -1, right. So outside of my bracket, so I'm actually going to close my top bracket. And I'm going to subtract 1 on the outside. So this is just notation reasons, but if you are multiplying anything to any function, it goes on the left of the brackets. If you are adding or subtracting anything outside the brackets, it goes to the right. All right, that's a notation thing, and yes, it does make a difference. All right, it's all about attending to precision. So that would be your new function. All right, let's do one more together, then I'm going to let you try one on your own. So number 3. So f of x, that's our parent function, and we want it reflected over the x-axis and shifted left 2. So first off, what type of function is this going to be? Absolute value, good. The tail is obviously the absolute value symbol. All right. So I'm going to go ahead and write it out with my brackets, leaving enough space in case I need to write anything in front of it or beside it. All right. And the reason I do this, guys, is just so I know where my brackets are so I can make that determination of where I need to put things. All right. If you're comfortable enough that you don't need to do this, that's fine. But this just kind of helps so you can clearly visualize where the brackets are. All right. So first off, we're reflecting over the x-axis. We just talked about this. That means we're dealing with a negative. Where is that negative going? Inside or outside? Outside. So remember, if it's reflecting over x, that means the y's are what's changing. So the y's are changing, it's always going to be on the outside. That's another way you can remember it. If the y's are what's changing, it's on the outside. If the x's are what's changing, it's on the inside. All right? That works for all the type of transformations. All right? So, and that's something you can ask yourself when you read these. Okay? So, that minus is going outside of this bracket. And remember, it's going to be on the left because technically we're multiplying it to it. We're multiplying it to it by -1. Now, it's also going to go left 2. So, left 2. First off, what value does that affect, the x or the y? It affects x. All right, left, right, x-axis. It's horizontal. Is it going to be inside or outside the brackets then? Inside. Plus or minus? Plus. And we're done. So this is my new function. Does that make sense to you guys, like how that works? All right, take a minute, try number 4 on your own. So first off, just for identification's sake, what type of function is this? It's a what? A cube root, good. All right, so this one's fairly quick because there's only one transformation happening. One transformation. Cube root. Because it has that little 3 in the upper right or the upper left. Square root would not have a number there.
Oh, I didn't see that.
All right, thumbs up if you're ready. Give you guys another minute. Ladies, if you can't handle it, I'll separate you. All right. Can someone tell me what they got as their answer? Good Lord. All right. So, what'd you guys get? First off, we're shifting up 3. So is that going to be inside or outside the brackets? Outside. And what operation would it be? Adding. So you should have gotten this. So
Oh, wait, I see it.
outside the brackets just means it's not under this radical. If it was inside, this radical would cover all of it. Okay. All right. So like I said, the logarithmic ones we're not going to worry about. But the rest of these on this page, that's going to be part of your optional assignment for 1.1. All right. Now we're not quite done yet. I want to do like 1 or 2 examples of going the opposite direction. So from equation to words. So turn to page 5. You should see this table. Well, these desks are also older than me. So that gum's probably older than me. Like they're literally older than me. They were bought in the 90s. I was born in 2000. All right. Shh. You're on page 5. We're looking at this table. All right. So now we're doing the opposite. We're starting with the functions, but we have to name the transformations. All right. So first off, they want us to name the parent function. So look for the tell for number 1. What is our tell here? What type of function this is? What would the tell be? The square. Right. So since the square is our tell, that means we have a quadratic. All right. Now, we're going to go down the line like it's listed on your graphic organizer. So we're going to start with horizontal transformations or horizontal. Yeah. All right. Yeah. Yeah, that. All right. So this one is a little bit weird because technically speaking, if you have a 2 right here, okay, that also affects this 1. So in reality, our horizontal will be a little bit different than what it actually looks like. So you'd actually have to divide the parentheses, the 2 out. So this would look like 2 times x plus 1/2 squared minus 4. And the reason I do this is because this assumes that we multiply the 2 in already. All right? It's like just a thing that you have to do. Now, that being said, now what is my horizontal translation? So where am I looking at? Horizontal affects what? X or Y? Horizontal. X. So would that be inside or outside my brackets? Inside. So looking inside my brackets, what's going on? Son of a biscuit. Can't connect to internet. What? Ugh.
Darn, guess we can't take notes. Shucks.
Well, this means you're doing work then.
Oh, can I do Delta math? No, can we do Delta math? Yes, come on. Huh? Oh, we're
Is it gonna make me put in? Crap. Oh, this is an easy fix. We're gonna do this once today. You will in just a second. I just need to do this one.
Do you have fourth period?
No. It's my planning.
Why can't you just leave?
Because I'm paid to be here till at least 3:20.
3:20.
Also, I need that planning period. Coming up with lessons just don't happen out thin air. All right, so horizontal translation. What is going on here? So we're looking inside the brackets. We know it's going to be either added or subtracted. So right here. So what's going on? First off, what direction is it going? Left. How many units? A half. So we shift left a half. All right, that's it. Now, dilations. So right here. Now, the reason it doesn't really matter with the dilation is because it'll do the same thing either way. All right? But now that it's outside the brackets, what type of dilation is it? Vertical or horizontal? So outside means that it's affecting what value? The y, so it's vertical. Now, it's bigger than 1, so will this be a vertical stretch or compression? A stretch, good. So we vertically stretch by what factor? What were we multiplying by? 2. So stretch by 2. Now, do we have a reflection going on? That's the next step. Is there anything being multiplied by a negative? Multiplied. No. So there's no reflection. Lastly, vertical translation. So up, down. All right. Do I have a vertical translation? First off, would it be inside or outside the brackets if I'm translating vertically? Outside. Because vertical, y-axis is vertical. That's how you can remember it. Okay? What is it? It's where the -4 is, but what's it doing? Is it shifting up or down? Shift down 4. All right. So we're going to stop here for today. I will post what all your optional assignment is for this packet, but we're pretty much done with transformations. Any questions on this? All right. So you guys got a solid 20-ish minutes to work on delta math. So you have the 1.21 and you now have a 1.11, which will be tentatively due Tuesday by midnight. So next Tuesday by midnight.
So wait, if we don't finish it, the first one by like 11 tonight, we just finish it like when we did it.
Before the unit test, yes.
Okay, but it's not going to be like kind of late though, right?
No. No, it's not counted late. So what I do sometimes is that I'll go ahead and put the grade in as it is, but then at the end of the unit, I go back and recheck it all.
Oh, okay. So I don't have to get, like if I get behind, like I don't have to turn it until the end of the unit.
Yeah.
Okay.
Technically, you got until the end of the term, but